A raindrop falls from a cloud about 2 kilometers up. 2 kilometers, that is higher than 6 Eiffel Towers stacked on top of each other. You with me? Good. Take any object, I do not care what it is, a baseball, a marble, a brick, drop it from 2 kilometers with nothing in the way. And by the time it reaches the ground, it is moving at about 200 meters per second. That is roughly 450 miles per hour. That is faster than a Japanese bullet train. That is faster than the takeoff speed of most commercial airplanes. That is in the neighborhood, the rough neighborhood of the muzzle velocity of certain handgun rounds. So let me ask you something. Every raindrop in a thunderstorm starts its life way up there. Some rain clouds sit at 3 kilometers, 4 kilometers, even higher. And each one of those droplets is pulled downward by exactly the same force that would yank a bowling ball off a bridge. Gravity does not care what you are made of. Gravity does not look at a raindrop and say, "Oh, you are small, I will go easy on you." Gravity grabs everything the same way. 9.8 meters per second squared. No exceptions. So by all rights, you should be getting machine gunned every time it rains. A spring shower should put you in the hospital. A thunderstorm should be a war zone. Every single droplet, pulled for thousands of meters by the full strength of Earth's gravity, ought to hit the top of your head like a tiny liquid bullet. And yet, you walk outside in a rainstorm, and what happens? You get wet. That is it. You get a little annoyed maybe because you forgot your umbrella, but nobody is calling an ambulance. Nobody is running for the bunker. You stand there, rain pattering on your shoulders, and you feel almost nothing. That is insane. Think about what I am telling you. The math says the rain should kill you. Your daily experience says it is a minor inconvenience. Somebody is wrong. Either the math is broken, or your experience is lying to you, or there is something else going on, something big that we have not accounted for. Let me show you which one it is, and I promise you, the answer is one of the most beautiful negotiations in all of physics. Let us start with what we know for sure. Let us be very careful about this, because careful is how you avoid fooling yourself, and the easiest person to fool is yourself. Gravity near the surface of the Earth accelerates everything at the same rate. Galileo figured this out a few hundred years ago, and it has been confirmed so many times and in so many ways that we can treat it as rock solid. The acceleration is about 9.8 meters per second. That means every second you are falling, you pick up another 9.8 meters per second of speed. After 1 second, you are going 9.8. After 2 seconds, 19.6. After 3 seconds, 29.4. It just keeps climbing. So you can do the calculation. A raindrop forms in a cloud, call it 2,000 meters up. If gravity is the only thing acting on it, you use the formula. The final speed equals the square root of 2 times the acceleration times the height. Plug in the numbers. 2 times 9.8 times 2,000. That gives you about 198 meters per second. Round it to 200. 200 meters per second. How fast is that, really? Well, the speed of sound in air at sea level is about 343 meters per second. So a raindrop, if gravity were the only thing pulling on it, would hit the ground at a bit more than half the speed of sound. Not quite supersonic, but absolutely terrifying. A small rock moving at 200 meters per second would go clean through a car windshield. A raindrop at that speed would not feel like rain. It would feel like being pelted with gravel fired from a slingshot. Millions and millions of tiny impacts every second, each one carrying enough kinetic energy to sting, to bruise, to break skin. And it would be worse than that, actually. Because I picked a modest cloud height. Some cumulonimbus clouds, the big thunderstorm ones, have bases at 3 or 4 kilometers, and tops that go up to 12 or 15 kilometers. The rain falling from those heights in a vacuum would be going even faster. You would need armor. So this is where we stand. Step 1 of the physics says rain should be lethal. Step 2 of your everyday experience says rain is not lethal. Something is deeply wrong with step 1. And what is wrong with step 1 is not a mistake in the math. The math is perfect. What is wrong is the assumption. We assumed gravity was the only force. We threw the raindrop off the top of a 2-kilometer cliff and pretended there was nothing between the cloud and your head. But there is something between the cloud and your head. There is air. You might think air is nothing. You walk through it, you breathe it, you barely notice it. But let me tell you something. Air is not nothing. When air is a real physical substance with real mass and real density. A cubic meter of air at sea level weighs about 1.2 kilograms. That does not sound like much, but there is a lot of air between you and the clouds. And when something tries to move through air at high speed, the air does not just politely step aside, the air fights back. Think about sticking your hand out the window of a car on the highway. At 60 miles per hour, the push of the air against your flat hand is surprising. Your hand wants to fly backward, you have to work to hold it there. That push is air resistance, and it gets dramatically worse the faster you go. It does not just double when you double your speed. It goes up as the square of the speed. Twice as fast means 4 times the drag. 3 times as fast, 9 times the drag. 10 times as fast, 100 times the drag. This is a very important fact, and it changes everything about falling rain. Now, I want you to really appreciate why the velocity squared business is not just a formula someone wrote down. It tells you something true about how the air interacts with moving objects, and it is wonderfully intuitive once you see it. When a raindrop moves through the air, it has to shove air molecules out of the way. The faster the drop moves, the more air molecules it encounters per second. That is one factor of velocity. But each of those molecules also gets hit harder because the relative impact speed is higher. That is the second factor of velocity. Multiply them together and you get velocity squared. It is not a coincidence. It is not an arbitrary mathematical form. It comes from the simple geometry of how many molecules you hit and how hard you hit each one. This means that at low speed the air barely notices you. At modest speed you feel a push. At high speed the air becomes a wall, and that wall is what catches every raindrop between the cloud and the ground. Here is what happens. A raindrop forms up in the cloud. But ding! It is tiny, just sitting there in the mist. And then it gets heavy enough that gravity pulls it loose. It starts to fall. At first it is moving slowly, very slowly, and at that speed the air resistance is almost nothing. Gravity is king. The drop accelerates at nearly 9.8 meters per second squared, just like any object in free fall. But as the drop picks up speed, something starts to happen. The air begins to push back. The faster the drop moves, the harder the air shoves against it. The drag force grows and grows. Meanwhile, gravity stays the same. Gravity pulls with a constant force equal to the weight of the drop. It does not get stronger just because the drop is moving faster. But the drag does get stronger, much stronger, because drag goes as velocity squared. So the drop accelerates, and the air pushes back harder. The drop accelerates more, and the air pushes back even harder. The net force on the drop, which is gravity minus drag, starts to shrink. The drop is still speeding up, but it is speeding up less and less. The acceleration is falling, and then at some particular speed, the drag force becomes exactly equal to the gravitational force. The two forces perfectly balance. At that instant, the net force on the drop is zero. Newton's second law says, if the net force is zero, the acceleration is zero. If the acceleration is zero, the velocity stops changing. The drop has reached its maximum speed. This speed has a name. We call it the terminal velocity. And it is one of the most important ideas in all of the physics of things moving through fluids, whether that fluid is air or water or oil or anything else. Terminal velocity is not something the drop chooses. It is not a speed limit imposed by some traffic law of physics. It is the natural consequence of two forces, one constant and one that grows with speed, fighting each other until they reach a draw. It is a negotiation, and both sides get exactly what they can sustain. Gravity says, I pull this hard, and I cannot pull harder. Air says, if you move at this speed, I push back exactly that hard. Neither side wins, they settle, and the drop falls at a steady constant speed from then on. So what is that speed? How fast does a raindrop actually go? This is where the details get lovely, because the terminal velocity depends on the drop itself. It depends on the mass, the size, the shape, and the drag coefficient of the raindrop. And these are not all the same for every drop. Let us think about mass first. A bigger drop has more mass, which means gravity pulls on it harder. More weight means you need more drag to balance it. More drag only comes at a higher speed, so bigger drops fall faster. A tiny drizzle droplet, the kind you can barely feel on your face, maybe 0.5 millimeter across, reaches terminal velocity at about 2 meters per second. That is a slow walking pace. You could almost keep up with it. A typical raindrop, the kind you see bouncing off the pavement in the steady rain, might be 2 or 3 millimeters across. That one reaches terminal velocity at about 6 or 7 meters per second. Quick, but nothing dangerous. A big fat raindrop, the kind that splats loudly on a windshield, might be 4 or 5 millimeters across. That is about as big as raindrops get, and we will talk about why in a moment. That one falls at about 9 meters per second, which is roughly 20 miles per hour. 20 miles per hour from 2 kilometers up, gravity wanted to deliver it at 450 miles per hour, and the air calmly negotiated that down to 20. Think about how dramatic that is. Air resistance takes a potential killer and turns it into a gentle tapping on your umbrella. The atmosphere is not just the thing you breathe, it is a shield. A soft, invisible, ever-present shield that slows down everything that falls through it. But wait, I want you to understand something subtle here, because this is where people get confused. The raindrop does not slow down. I want to be very precise about this. If you drop a raindrop from a cloud, it never actually decelerates on the way down. It speeds up and then it stops speeding up. It reaches terminal velocity and then falls at that constant speed the rest of the way. It does not speed up and then slow down. It speeds up and then stops accelerating. There is a big difference. One means the drop is losing energy. The other means the forces are in balance. What is happening is the second one, and here is the beautiful part. For a typical raindrop falling from a cloud at 2 kilometers, it reaches terminal velocity within the first 100 meters or so of falling. After that, it has another 1900 meters to go, and it is falling at this gentle cruising speed the entire way. It is coasting. The vast majority of the drop's journey is spent at terminal velocity. The brief acceleration phase is over almost before it begins. So the image of a raindrop being dragged faster and faster and faster for 2 solid kilometers is completely wrong. The reality is that it gets a short running start, reaches its top speed very quickly, and then drifts lazily downward for the rest of the trip. And there is a beautiful energy story hidden in here that I think most people miss entirely. Think about what is happening from the perspective of energy. And that gravity is doing work on the raindrop the entire time it falls. The drop loses potential energy as it descends, and that energy has to go somewhere. In a vacuum, all of that potential energy would be converted into kinetic energy. The drop would get faster and faster and arrive at the ground with a tremendous amount of motion energy. But in air, once the drop reaches terminal velocity, it is not gaining kinetic energy anymore. Its speed is constant, yet gravity is still doing work on it. Where is all that energy going? Into the air. Every meter the raindrop falls at terminal velocity, it is doing work against the drag force. That work heats the air ever so slightly. It creates tiny turbulent eddies in its wake. It jiggles air molecules. The potential energy of the raindrop is being converted not into the raindrop's own motion, but into thermal energy of the atmosphere. The air is absorbing the energy that would otherwise make the raindrop dangerous. A single raindrop releases a very tiny amount of heat this way. But think about a thunderstorm that drops, say, 50 millimeters of rain over a large area. Billions upon billions of drops, each one converting gravitational potential energy into heat in the atmosphere. The total energy transfer is enormous. It is one of the many ways that weather redistributes energy around the planet. The rain is not just bringing water down, it is bringing energy down, and the air is soaking it up on the way. Now I want to show you something else that most people get wrong, and it is a delightful thing to get wrong because the truth is so much more interesting than the myth. I am talking about the shape of a raindrop. Ask a child to draw a raindrop and they will draw a teardrop. Pointed at the top, round at the bottom, like a little liquid flame. You see this shape everywhere. Weather reports, decorations, cartoons, logos. Everybody knows what a raindrop looks like, and everybody is wrong. A small raindrop, less than about a millimeter across, is a nearly perfect sphere. It is a tiny round ball. Surface tension holds it together, the same force that makes water bead up on a waxed car. The water molecules on the surface are pulling inward, trying to minimize the surface area, and the shape with the least surface area for a given volume is a sphere, so small drops are round. As the drop gets bigger, gravity and air resistance start to compete with surface tension. A drop 2 or 3 millimeters across is still roughly round on top, but the bottom gets flattened. The air rushing past underneath pushes up on the bottom face. The drop starts to look like the top half of a hamburger bun. Rounded on top, flat on the bottom, not a teardrop at all. The exact opposite of what you would expect. And when a drop gets really big, bigger than about 4 or 4.5 millimeters, something dramatic happens. The air pressure on the bottom creates a dimple, then a cavity. The drop starts to look like a tiny parachute or a jellyfish, with a thin film of water stretched across the top and a thicker ring of water around the rim. It is completely unstable in this shape. Within moments, the thin film ruptures, and the big drop explodes into several smaller drops. This is why you never see raindrops bigger than about 5 millimeters. Nature has a speed limit for raindrop size, and that limit is enforced by air resistance and surface tension working together. This breakup business is important because it explains something else. If all raindrops started huge, up in the cloud and grew as they fell, you might eventually get enormous drops hitting the ground. But they cannot survive. The bigger they get, the faster they fall, the more the air deforms them, and at some point they shatter. So the rain that reaches you is always in this narrow range. Not too small to fall, not too big to hold together. Nature has filtered it for you, and every single one of those drops, regardless of size, has found its terminal velocity long before it reaches the ground. Let me come back to the physics for a moment, because I want you to see the machinery that makes this work. The drag force on an object moving through a fluid depends on a few things. First, it depends on the density of the fluid. Denser fluid means more drag. Swimming through honey is harder than swimming through water, and swimming through water is harder than moving through air. Second, it depends on the cross-sectional area of the object, the area it presents to the flow. A parachute has more area than a marble, so it gets more drag. Third, it depends on the speed squared, as we talked about. And fourth, it depends on something called the drag coefficient, which is a number that captures the shape and smoothness of the object. A sleek sports car has a low drag coefficient. A brick has a high one. A flat plate perpendicular to the wind has an even higher one. For a roughly spherical raindrop, the drag coefficient is about 0.5. That is somewhere between a smooth sphere and a rough one. It is not a bad number. Nothing exotic. Just an ordinary shape doing its ordinary thing in ordinary air. Now let me do a thought experiment that makes the formula come alive.